Hello everyone. Today we are starting with Mathematics and Statistics Part 2, Chapter 6, Differential Equations. Okay, now differential equations are based on derivatives, higher order derivatives, and let us begin with what do we understand by differential equations. Okay, so we represent the rate of change of y with respect to x as dy by dx, right? So if we have to represent any change in a quantity y with respect to x, then we say it as dy by dx. Okay, so rate of change of y with respect to x. That is, if x is changing, then how will y change? So we say dy by dx. Let x be the quantity, let's say for example, radioactive disintegrating element at time t. Okay, now it is found that the rate of decay of the material. Now whenever we say rate of decay, basically rate is d by dt. Now decay of the material means the material is x. Okay, is proportional to the quantity of disintegrating substance. So x is a disintegrating substance, so let's say it is proportional to x. Now dx by dt is degrading, that is decaying. Okay, so if I have to remove the proportionality sign, I will put a minus k constant. Okay, and why minus k? Why negative? Because dx by dt is reducing, that is the material is degrading. Here we have a relationship between dx by dt and x. This is called as a differential equation. Okay, now differential equation basically gives you relationship between the dependent and the independent variable. Okay, so an equation which contains one independent and one or more dependent variables and their derivatives or the differentials. Okay, so basically you have the function and then you have their derivative. So you can have dx by dt square, you can have d3x by dt square, or they're also called dt cube. They're also called as differentials. Dx or the differentials dx dy is called a differential equation. The following are some examples. So you could have y square dx, okay, minus say plus x square dy equal to 0 as your differential equation. Not necessarily always it has to be equal to 0. You can take the terms on the left side and then make them equal to 0 though. A differential equation in which the dependent variable y depends only on one independent variable x is called as an ordinary differential equations. In this chapter, we'll be studying only ordinary differential equations where a dependent variable y is dependent only on one independent variable x. Okay. Following notations are used for derivatives. So derivatives normally we have higher order as d2x by dt square is normally given by y double dash. This could be your, you can say x double dash here, because since it's a function in x and dt. So this would be y double dash x double dash here, and here you can say x triple dash. Okay, so let's say we have a function like dy by dx, then this, if this is y, then, or you can say if this is the first derivative, then the second derivative is given by y double dash d2y by dx square, and y triple dash when it is d3y by dx cube. Okay, so that is your derivatives, higher order derivatives. If y is equal to f of x, then we have f dash of x, f double dash of x. Okay, so what is f dash of x? First order derivative, f double dash second order derivative, and so on. Now order and degree of the differential equation. Order and degree of a differential equation. What is the difference between the two? So let's say we have a differential equation d2y by dx square plus x dy by dx plus y equal to 2 sin x. Now in this we have to find out first of all the order and the degree. Now order is basically the value of the highest order derivative. Okay, so which is the highest order derivative over here? d2y by dx square. So you'll say that highest order derivative is d2y by dx square. Therefore, order will be 2. So whatever is the highest order derivative, that is the order of the equation. Now what is degree then? So degree will be the power to which the higher order derivative is raised. Okay, so here the higher order derivative is not raised to any power. If you can see, it's raised to 1. Okay, so if this is raised to 2, then the degree would be 2. If this is raised to 1, then the degree would be 1. So for this equation, the degree is 1. Okay, so you can say degree for this equation is 1 and order for this equation is 2. So order is basically the highest order derivative and degree is the power of the highest order derivative. Okay, that's how you will differentiate between order and degree. Now, the definition of degree is also that it is the power of the highest order derivative occurring in a differential equation when it is written as a polynomial of differential coefficients. So if when only you can write it as a polynomial, that is in decreasing order of the derivatives and differential coefficients, then you can call it as a differential equation and you can give it its degree. Okay, starting with exercise 6.1, determine the order and degree of each of the following. The first one I just did for you. I'm doing the second one now. So the second one is cube root of 1 plus dy by dx the whole square equal to d2y by dx square. Okay, now you have to observe the question first. It has a cube root sign. So first of all, we have to remove all the root signs. So let's cube on both sides. So we'll get 1 upon 1 plus dy by dx the whole square, right? Equal to d2y by dx square the whole cube. Okay, now what is the order? The highest order derivative here is d2y by dx square. So the order is 2. And what is this order raised to? So what is the degree? 3. So order is 2 and degree is 3. Okay, moving on to the next one. I'll do the fourth one now, then we can go to the next topic. This is simple, order and degree. d2y by dx square plus dy by dx plus x is equal to under root of 1 plus d3y by dx cube. Okay. So we'll take the question and square it on both sides since there is a root sign on the right side. So this will be d2y by dx square the whole square. That is the entire thing we have to square. So we'll just write a square here. Okay, equal to 1 plus d3y by dx cube. Okay, now what is the order again? So order is the highest order derivative, that is 3. If you can see on the right side, it is 3. And then what is the degree? What is this highest order derivative raised to? 1. So degree would be 1. Okay, this is your fourth question. Now I'll do the seventh one because that's a little different. Okay, so the seventh one here is d2y by dx square. Okay, the whole thing raised to 2 plus cos of dy by dx is equal to 0. Now in this case, this equation definitely has a order. Okay, so order would be 2 because the highest order derivative is 2. But the differential equation that we have over here cannot be expressed as a polynomial of differential equation, differential coefficients. We cannot do that because if you observe it is cos dy by dx, cos does not have a variable. It has the derivative itself inside it. And so it cannot be expressed in the form of a polynomial. So we cannot say about its degree, or we can say degree is not defined. Okay, so this is the reason why I took up this sum. You need to know when to write the degree and when to write whether it's not defined. Okay, let's move on to the next topic now. I've done some sums from the exercise 6.1. They're all based on order and degree of an equation. Okay, now the next topic is the formation of differential equations. Now, how do you do the formation of the differential equations? If a relationship between x and y is given to you with some arbitrary constants, then we can form a differential equation from it by differentiating the given relation enough number of times as to eliminate the arbitrary constants. Okay, so let's say that we have an equation, say y square equal to bx. Okay, then we differentiate this equation as many number of times as we can eliminate the arbitrary constants. Now, how do you know how many times to differentiate? So it depends on the number of arbitrary constants. Here we have b as our arbitrary constant. So if we have to eliminate this, then I write 2y dy by dx, okay, is equal to b. And then what do? I substitute this in place of b, that is 2y dy by dx into x, okay, which is y square equal to 2xy dy by dx. And then you can take it on the left side, write it as y square minus 2xy dy by dx equal to 0, and that becomes your differential equation. Okay, so basically to form any differential equation you have to take your equation, remove its arbitrary constants, resubstitute them and write the equation. Okay, so let us try and find out how to do these differential equations, formulate these differential equations. So exercise 6.2, question 1, first one. We have an equation over here, x cubed, one second. Exercise 6.2, the first one. So we have an equation x cubed plus y cubed equal to 4ax. Now here the arbitrary constant is only a, so we differentiate only once. So we'll say differentiating with respect to x, and this will be 3x square plus 3y square dy by dx, right, is equal to 4a. And now what I'll do, I'll mark this as equation 2 and this as equation 1 and substituting 2 in 1. Okay, why substituting 2 in 1? I told you we have to remove the arbitrary constant 4a. Okay, so substituting 2 in 1. Okay, so let us put the value of 4a. What will we get? So 3x square plus 3y square, sorry, one second. To substituting 2 in 1, we would get x cube plus y cube equal to 4a, so that is 3x square plus 3y square, okay, dy by dx, whole thing multiplied by x, and you can take x on the left hand side, okay, or open this bracket. Now if I open this bracket, what do I get? X cube plus y cube, okay, is equal to, what's the first term? 3x square, so that becomes 3x cube, okay, plus 3xy square dy by dx. Okay, taking all the terms on one side, so x cube minus 3x cube would be minus 2x cube, okay, minus 3xy square dy by dx plus y cube equal to 0. Okay, and then removing the minus sign, so I will get 2x cube plus 3xy square dy by dx minus y cube equal to 0. This is your differential equation. Okay, now I'm doing one sum with two variables, so ax square plus by square equal to 1. Just a general equation, it is second sum. Okay, so the second sum, ax square plus b y square equal to 1. Okay, differentiating both sides with respect to x. Let's begin. So this will be 2ax plus 2by dy by dx equal to 1. We call this is equation 1, this is equation 2. Okay, now again we will differentiate this equation. So differentiating with respect to x again. Okay, so we get 2a plus 2b, and now y dy by dx, how do you differentiate? So basically you use the multiplication rule. Y first term as it is, differentiating the second one, so d by dx of dy by dx, so that is d2y by dx square, okay, minus second term as it is, differentiating the first one, that is 1, sorry, plus minus dy by dx, sorry, not 1, dy by dx would be the differential of y equal to 0 here also and here also. Okay, therefore we'll get an equation in a and b. Let us remove the 2 common, so we get 2 outside, we get a plus b, and we have a bracket here, y d2y by dx square plus dy by dx the whole square, y d2y by dx square plus dy by dx the whole square, okay, equal to 0. Okay, now we have a as a equal to minus b y d2y by dx square plus dy by dx the whole square. Okay, we'll substitute the value of a in our first equation, that is, sorry, in our second equation. Okay, so we'll call this 3 and we'll say substituting 3 in 1. Okay, so in 2, not 1. So what is our second equation? It says 2ax plus 2by dy by dx. Okay, so we have 2, instead of a, what do we have to write? Minus b minus b d2y by dx square plus dy by dx the whole square, okay, into 2ax, okay, plus 2by dy by dx equal to 0. You can take 2b common. Okay, so we have minus d2y by dx square into y minus dy by dx the whole square into x plus y dy by dx equal to 0. Okay, you can remove the minus sign. So your final equation is xy d2y by dx square, okay, plus x dy by dx the whole square minus y dy by dx equal to 0. Okay, so that's how you would eliminate both the constants and get your answer. Okay, this was the second sum of exercise 6.2. Now all the sums in 6.2 are almost the same. I'll do the fifth one now. Okay, question 5. Y equal to a e raised to 5x plus b e raised to minus 5x. Okay, Now here you can see that there are two constants. So let us see how to eliminate both of them. So differentiating with respect to x, you can say 2 times already, so don't have to write it again. First differentiation, so dy by dx is equal to a e raised to 5x into 5 minus b e raised to minus 5x into 5. So I've directly put that minus sign there. Okay, you can have again the differentiation, so d2y by dx square is equal to 25 a e raised to 5x plus 25 b e raised to minus 5x. Okay, what we'll do is we'll take 25 common, so you'll get 25 in bracket a e raised to 5x plus b e raised to minus 5x. What is this? The question itself, right? So you can write d2y by dx square is equal to 25y okay, take it on the left side, so d2y by dx square minus 25y is equal to 0. This is your required equation. Okay, this is how you would formulate your differential equations. That was your question 1. Moving on to question number 2 now. So from question 2, form the differential equations of families of lines having intercepts a and b on the coordinate axis respectively. Now, equation of families of lines. Basically, first we should know that if you have intercepts a and b, then how do you represent the family of lines? So we should know these equations for at least this chapter. So representing them as x upon a, so question 2, x upon a plus y upon b is equal to 1. This is the family of lines with intercepts a and b, okay, where a and b are arbitrary constants. For different values of a and b, we get different lines. Hence, that is called as the equation for family of lines. Now, we'll differentiate this equation, okay. Since there are two coefficients, so we'll say differentiate with respect to x 2 times, okay, which will be differentiation of x will be 1 upon a, okay, into 1 plus dy by dx, so 1 upon b into dy by dx equal to 0. Okay, let's differentiate, or you can say 1 upon b dy by dx is equal to minus 1 upon a, and so dy by dx is equal to minus b by a. Okay. Differentiating this with respect to x again, second differentiation is yet remaining. You have to differentiate it if you have two variables. Okay, so this will be d2y by dx square is equal to 0. Okay, so what do we observe here? That for a family of lines, the differential equation is second derivative equal to 0. Okay, let's go to the question 3rd now. Find the differential equation of all parabolas having length of latest rectum as 4a and axis is parallel to the x-axis. So now this parabola here that they are talking about is drawn with the help of another axis which is parallel to the x-axis. Okay, and latest rectum value is 4a. So let's draw the diagram for the same. So let's say this parabola is, its axis is over here. So it's supposed to be in this manner. Okay, let's see. Okay, and here it says that it is parallel to the x-axis. Okay, the axis is parallel to the x-axis and having length of latest rectum as 4a. Okay, so latest rectum is 4a If a h comma b k be the vertex, now here vertex of the parabola is not mentioned. Okay, so that is why we are taking it as h comma k. If it is mentioned it is 0 comma 0, then you have to take it as 0 comma 0. So if there is a general parabolic equation, then how do you give it? Like you gave general equation for line, so you have general equation for parabola as y minus k the whole square is equal to 4a into x minus h. Okay, because your general equation for a parabola is y square equal to 4x, where this parabola is intersecting the origin at that is 0 comma 0. Okay, so we get the equation as y square equal to 4ax. K and h is 0 comma 0. If that is not the case, if you have a general parabola whose vertex we are not knowing, or it is of a particular value, then it is given by y minus k the whole square is equal to 4a into x minus h. Okay, now here we can see that we have h, k are arbitrary constants. So let us differentiate this equation with respect to x and see what we get. So here our arbitrary constants are h and k. 4a is the radius rectum, that is a fixed value. Okay, like say a constant 4, 5. Hk could be changing, and that's why our arbitrary constants are h and k. Okay, now the differential equation here would be 2y minus k dy by dx. Okay, equal to, sorry, 1 second. Okay, let us differentiate this equation now. So we'll get 2y minus k into d by dx of y minus k. Okay, equal to 4a, and x minus h derivative would be 1 minus 0. Okay, now this will be 2y minus k into dy by dx equal to 4a. Y minus k dy by dx is equal to 2a. Differentiating this equation with respect to x again. Okay, so we'll get first term as it is, derivative of the second, so d2y by dx square, plus second term as it is, derivative of the first, so that is dy by dx, and the right side would be equal to 0. So we get y minus k d2y by dx square plus dy by dx the whole square equal to 0. Now we need to find the value for k for substitution. So what we can do here is we can substitute the value as y minus k dy by dx. That means we can remove this as if you observe the previous equation that we got in the first derivative, we did not number it, right? So we'll just number that. This one as 2 and your original equation as 1. Okay, so from equation 2, what I can do is I can write y minus k as 2a upon dy by dx. That ways both my constants get eliminated. So from 2a upon dy by dx, okay, into d2y by dx square plus dy by dx the whole square equal to 0. You can take LCM and get dy by dx the whole cube as well. So your final equation will be 2a into d2y by dx square, okay, plus dy by dx the whole cube equal to 0. This is your final differential equation. Okay, so this is how you would find if you have the various equations of an ellipse, of a parabola, of straight lines. Use the equations, the standard equations, and get their differential equations. Okay, we'll stop here for this session. This is our first session for differential equations. In the next unit, next session, we would do solution of differential equations. If you have any doubts in these two exercises, do let me know. Thank you so much.